Okay, so welcome to Math 343, the Mathematics of Sports. So this is lecture 10. And what I want to do today is talk about, a little bit more about the consequences of position evaluation. We'll talk a little bit about football, and then we'll switch to some things for backgammon, and then talk about constrained optimization. So I'm waiting for people to finish up doing the analysis of single, double, triple home run so that we can have a really nice evaluation of which is worth more. And it's worth taking a step back and trying to think, what are we trying to do? The idea is that we have a couple of interesting configurations where you might actually have two players with the same slugging, the same batting average, the same on-base percentage, but they're not equally valuable. So this gives you the opportunity of saying that just because some items agree with these metrics does not mean that they're actually equivalent, that I can look at something else in addition. So your slugging percentage, your on-base percentage, your batting average does not uniquely specify your worth to the team. And again, we're holding off things such as, are you a nice teammate? Which can be an extremely important factor. We're just looking at offensive characteristics. And so single, double, triple home run, they're valued in a certain way with these statistics, but that may not be the best way to evaluate. And we've talked about how to answer which are the correct values to assign to them. And for that, we need some data. Now, we haven't talked about the value of a walk. Is it easy to calculate the value of a walk? Can we figure out the game state transitions, right? So what's the game state transition for a walk? Who can phrase it nicely?
Everyone moves forward one.
So everyone always moves forward one with a walk?
Unless there's no one behind them.
Right, so starting with, any runner on first moves forward one, any runner on second moves forward one if there's a runner on first. So as long as there's a chain from you with no gaps to first, you all move forward one. Do you always move just one? Yes.
It would technically steal second on a walk. Like if it's a wild pitch.
So if it's a wild pitch. So there are some interesting configurations where you can get an extra base. I know years ago, the Dodgers were playing the Mets in the playoffs. There was a runner on first and there was a huge shift and they walked the batter. And the guy from first just, calmly walked to second and then ran to third because the shift was on and there was no one covering that side of the field. And then all of a sudden the defense realizes there's no one to throw the ball to. This is rare. It's so rare that there's so few situations I can remember that I'm not too worried about that. We can very easily figure out most of the time, this is the value of a walk, this is the value of a hit by pitch. What is a little bit more difficult to figure out, and we'll deal with that later, is the different types of outs. So what's a good type of out? What's a good type of out?
Strikeout.
So a strikeout in some sense is good in that it's not going to get you into a double play. A double play is a really bad out, right? So there could be, you actually don't get credit for an RBI if it's a double play, but it might still be strategically valuable for you to get.
You need a good out for the batter.
A good out for the batter. Sac fly. So if you hit the ball deep to the outfield, you might be willing to trade the out for the guaranteed run or to move a runner up. And so when we're looking to figure out what is the value of a batter, we should also look at the contributions from the different types of outs. Keep it simple. First, let's just answer how valuable is the walk, hit by pitch versus single, double, triple home run. And then once we have that, then let's try to figure out what happens if we add this type of outs. We need more information about the players. We need to know how many sacrifice flies do they have? How many fielder choices do they have? And these things can become important. So again, we're trying to figure out the relative value of different configurations that lead to the same numbers. And so this is going to get to the last item, constrained optimization. If I know I have a certain feasible set of solutions, I want to pick one of them that's best for some other metric. And so I could have multiple ways of having the same slugging on base. I could have a double and a triple versus a home run and a single. Which is better? And we've talked about how to answer that by looking at these run expectancy matrices and the probabilities of being in the different configurations. So that's going to be a big theme now, is this constrained optimization. Okay, football. So I'm not going to go through all the details, but there is a huge literature now on, do you go on fourth down? One of my favorite quotes, and I probably should have put in, people familiar with demotivation posters? Like one of them is the picture of the Titanic sinking, and it's titled "Mistakes. Maybe the purpose of your life is to serve as a warning to others." And so there's a whole slew of these. One of them is, the tall grass feels the blade first. If you do something different and stand out, when something goes wrong, they know who to blame. And so a lot of people, they don't play to win. They play so as not to be blamed for the loss. I think I might have mentioned, years ago, Belichick and the Patriots were playing the Colts. And if the Patriots had converted on fourth down, they could have run out the clock. They didn't. The Colts got back the ball with a short field, and Manning drove down. And he said, hey, I did what I did because I thought it increased the chances of winning. And the computer simulations actually supported what he did. It did increase by a couple of %. But a lot of people are afraid to do the non-standard thing. And so doing, just a quick search online, I found, an article talking about when should you go for it on fourth down, when should you punt, when should you go for the field goal. Well, not surprisingly, if you're deep in your own territory, you're not going to go for the field goal. And then eventually gets to the point where, if it's, I think this is 4th and 1. Oh, no, 4th and 1 is at the top. In 4th and 15, basically don't go for it on 4th and 15. Kick the field goal when you're somewhat close. And then the interesting thing is how close people's strategy is to what is optimal. I'm a little bit concerned about some of these white splashes here and over there. How would you read this strange discontinuity? I would not expect something like that. Yeah. Yeah. Happened once, and there was one coach who found themselves in that configuration, and so they went for it. So maybe the whites might indicate places where we have no data. Again, whenever you see an image, always think about what's going on. When I see stuff like this, maybe we never actually had somebody in 4th and 13 at their own 10. And so if this is the case, it looks like, if you can trust the results on the left, people are not making intelligent decisions. The other thing, of course, and this is going to be really important when we get to backgammon, is as soon as you know that you're going to go for it on fourth down in this configuration, how does that affect your strategy? What would you do differently if you know you're going for it on fourth down?
You don't have to go past first down on third down.
Right. So on the third down, I don't have to guarantee that I make it on third down. And so I might be willing to take, if it's, 3rd and 7, I might be willing to take a 5 or 6 yard gain and not have to, well, I've got to catch the ball beyond the first down marker, or it's a wasted play for me. And so that greatly changes then your probability of actually making it, because I now know I'm going to do it twice. And so to get values like this, we have to answer a fundamental question. This is something that's come up numerous times. What is the value of different configurations? What's the expected value? So if I have, 4th and 5 from my own, 40-yard line versus 4th and 5 from the 2-yard, well, maybe from the 2, from say the 5-yard line. how many points do I expect to get in each configuration for various things? If I go for it on fourth down, what do I expect the outcome of the drive will be? Well, I could hopefully get a touchdown. If not, maybe later I'll have an easier field goal attempt than what I have now. Or I might get stopped, but maybe I drive the ball further. And what's the advantage of driving the ball further, even if you don't get any points? Why does it make it tougher for the other team to score?
Turn the ball over on their 10-yard line.
Right, so if you drive the ball further down, they get the ball much further, or you might have better position to kick the ball. Sometimes teams will actually take a penalty deliberately for delay of game to get a little bit more space to kick so the ball doesn't go into. There's lots of subtleties and you can go crazy taking everything into account. But the main problem here is we need to figure out what is the expected number of points scored for different positions in a football game. And in baseball, we had the run expectancy matrix. We needed to know what was the configuration of base runners, what was the configuration of outs. What do you think we need to know in football? Calculate the point expectancy. What do we need to know? Down, distance, yard line, anything else, and time. So, the first time the Eagles played the Patriots in the Super Bowl, the Eagles were down by 2 scores and were running an extremely casual offense. And as a Patriots fan, we were thrilled to watch the Eagles just, killing clock time for plays up the middle. And so depending on how much time is left, that's going to greatly impact your expected ability to put up points. If there's not that much time left on the clock and you don't have many timeouts, very different than if it's early in the game. So when we're trying to figure out the expectancy, we need all that information. But we should be able to get this just like baseball. In baseball, you look at all the different times we had this configuration. Now in football, we have a lot more configurations. How many configurations do you want to have for where the ball is? Approximately how many?
Seems like too many.
So that's where things become interesting. So the first thought is, well, let's do 100, on each marker. But it's like, if we do that many, are we going to have too few data points? So maybe we cluster things into 2s and 3s or something, or even 4s. And that's something you have to think about in terms of, I want to have enough data so that these things are meaningful. And is there really much of a difference between having the ball on your own 36 or your own 35? It's really pretty similar. But there might be a huge difference between having the ball on your own 1 or your own 3. Right? What's the big difference between having it on your own 1 or your own 3? Risk of safety. So what you might do is you might not have all bins of equal size. So maybe from maybe from like the 40 to the 40, you might be able to have slightly larger bins. And then as you start getting in more and more and more, then it might become more important to have smaller bins. So these are things we need to think about, and we need to figure out what is the value of a given configuration. This is one of the big themes we've had. We've had some articles on chess, which we will probably talk about later. The big problem in chess is figuring out what is the value of some configuration. And I might have sent you a nice YouTube video where black just has far more material than white, but in this extremely contrived artificial example, white can actually force it so that white scores upon and black scores upon, but white scores, I think, in calls check. And so the black scored pawn of queen is useless and white can just keep picking things off. All right. How many people have ever played backgammon? All right. Cultural extra credit, what movie? Can't get the movie, at least get the franchise. James Bond. So it's from the movie Octopussy, which has a lot of my favorite Bond moments. And so there's a beautiful backgammon game there. And so right now, we don't need to know all of the rules of backgammon. All we basically need to know is it is a 2-player game. It is possible that the game could never end. because you can, white is moving in this direction, trying to get all of its white pieces down here. Black is moving in the other direction, trying to get all of its pieces in the upper right. If a white piece is jumped, it goes to the upper right, it needs to be moved back in. If a black piece is jumped, it comes to the bottom right, it needs to be moved back in. So it's possible if you keep jumping each other that the game might never end. And you want to figure out, when you roll your die, there's rules about how you can move your pieces. And it turns out there's something called the doubling die. I'm not going to go into too much detail on what the doubling die is, but initially a game starts off worth 1 point. And then either person can double and make the game worth 2. If I double and you accept the double, you now control the doubling die. And I can't double until you double. And then once you double, if I accept, then I control the doubling die. And so on and so on and so on. And so normally doubling dice go from 2 to 64. Why don't they go up higher? Yeah, it's a 6-sided die. This is basically what we can do, right? But you could still play with, say, look, my die only goes up to 64. If we actually hit 64, we're going to then just reset it. And now the 2 now means 128. And you can just keep playing like that if you want to allow unlimited doubling. What this means is that when you have a configuration of pieces on the backgammon board, you need to figure out what is the value of that configuration. So what is your probability of winning? What is your probability of losing? Now, how many of you do not know the rules of backgammon? Does anybody know the rules of backgammon? All right, so 3.5 maybe. So the question I'm asking does not require you to understand the rules of backgammon. Imagine you have this black box function that will return the probability of winning given a configuration. Okay, so your homework for the next class is to tell me, what do you think, and just email me, if I'm trying to decide, do I want to double, what should my probability of winning be for me to double? What should my probability of winning be for me to accept a double? Now, one of the things that makes this difficult is if I double and you accept the double, who wants to accept the double? All right, so you accept the double, you now control the doubling cube. So now if the game, let's hope I'm not an idiot. Okay, let's hope that I have at least a what % chance of winning. Can somebody say something to make me not an idiot? At least 50%, right? We're going to assume I'm not going to double when I'm losing. All right, so I at least have a better than 50% chance of winning, and I double. And now all of a sudden you roll really well and you have the lead. And now you have the doubling cube. So my danger now is by doubling, I give you the doubling cube. And so you could then double the game.
Once it's been doubled, I don't have to ask you to accept it. Like I can just do whatever.
You can do it whenever. And if I decline, then you immediately win the game. So that's the advantage of doubling. So let's say I have an 88% chance of winning. What does that also mean? I have a 12% chance of losing. This is like, would you rather hear you have a 95% chance that the surgery is successful, or there's a 5% chance that we will be saying nice words about you later this week? A lot of people like to focus on the positive. So if I have an 88% chance of winning, I have a 12% chance of losing. If I double and you accept the double, the game is now worth 2 points. If you decline the double, the game is over and I get 1 point. So one of the nice things about doubling is you've now eliminated the 12% of the time when the other person will come back. So the question is, what's the critical threshold? Where do you double? Now, what makes it complicated is that, let's say you have a 12% chance of coming back and beating me, and all of a sudden things start to go well for you, and now you have the doubling cube. But then maybe you double and maybe I accept and now things go well for me. So this process could go on infinitely often. Can somebody give me a modification that would make this a lot easier?
the game doesn't end if you define the double?
So what does it mean if the game doesn't end?
Or like, it would be easier if you don't force that option where the game would end.
Okay, so one possibility is that to make the game easier is there's no, so if you decline the double, the game immediately ends. So there's a huge advantage to doubling to scare someone out. You could say, of course, that the game doesn't end, but the real issue is that we could go back and forth with doubling, and I have to keep figuring out that whole analysis. So what would make things much easier than having to figure out this back and forth analysis? Good, a set amount of doubles. And what should that set amount of doubles be? Make life easy. Yes. No. No. What? One person can double. That's it. Right? If we can't even answer the question in that one case, we're not going to be able to get the general. And after we can do one, what's the next one? Two, right? So see what you can do if there's only one double, if there's only two doubles. And again, this is a general theme. Think simple. If you can't solve the simple problem, you're not going to get the more general. Now, there is a danger that when you look at a simple problem, you might, unfortunately, not see what's truly going on. You might focus on things that don't matter. And I can give some, nice proofs in advanced mathematics where it might look like certain items are really important. They're not. But it might look that way. So what I want to do now is I want to explain a new game. And this is a great example of constrained optimization. So given a number, let's say S, maybe it's 100. Write S as a sum of non-negative integers. I'll do A1 dot 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 AN such that A1 times A2 times dot 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 times AN is as large as possible. So, i.e., maximize the product A1 through AN given A1 plus AN equals S, and each AK is greater than or equal to 0 is an integer. And whenever you see constraints like this, you always want to ask, why am I putting some of these constraints in? So for example, I'm saying not just integers, but non-negative integers. Can anybody tell me why I want the integers to be non-negative? So can anybody tell me why I want the integers to be non-negative? So what would happen if the summons was not non-negative? What could happen? So give me an example. Let's say n equals 100. Give me an example. Because again, whatever I choose for the a's, they have to sum to that number s. So if I have a negative number, then it means I have to have other ones that are positive. So what's the first thing when you hear non-negative? What am I excluding? So when I say non-negative, what's the first thing that comes to mind that I've excluded? All negative, but there's something else that's excluded when I say non-negative. What else is excluded? Oh, wait, did I say non-negative? Oh, I'm sorry, I said non-negative. My fault. I don't want to say non-negative. What did I mean to say? That's my fault, not your fault. I meant to say not non-negative, but something very close to non-negative. Positive. So why wouldn't I want to have one of the summands be 0? If one of the terms is 0, then product is 0. If negative allowed, what could we do? How could I get, yes?
Just keep, say like negative a billion and then negative
Good.
a billion and one, you get bigger and bigger positive.
So I could do negative n, sorry, we're doing s. Negative ms plus 2m plus 1s. And I can make the product as large as possible. So product is as large as we wish. Okay, so if I were to allow myself to have negative numbers or 0, then the problem is stupid. You know, I can just make the product as big as I want, or I can make the product 0. I would never want the product to be 0. So clearly, I want my integers to be positive. So what I want you to do now is tell me constraints on the positives. The positive integers AK. Do you think any of the AKs would be 1? So we have A1 plus AN equals S. Again, we don't know what S is. Each AK greater than 0 is an integer. We want to maximize the product. Would we take it? Yes. Yeah, it doesn't help the product. So if AN equals 1, replace AN minus 1 with 1 plus AN minus 1 increases the product. And the sum is the same. So we clearly don't want any of the A's to be 1. So we're talking about trade-offs. What if one of the A's was 6? If had 6, we could replace with what? What could we replace 6 with that would have the same sum but a better product? So what could we replace 6 by that would have the same sum as 6 but a bigger product?
4 and 2.
4 and 2. And of course, if we had 7, we could replace with what? 5 and 2. If we had 8, we could replace with 6 and 2. So we clearly know we don't want any 6s. What if we went lower? What if we had 5? What could we replace 5 with? 3 and 2. What if we had 4? What if we had 4? What could we replace 4 with? Okay, it may not improve the product, but what could we replace 4 with? 2 and 2. And here we're indifferent.
Why would you not do like 5 and 3?
You could, doesn't matter. All I need to do is say there can't be any 8s in my optimal decomposition because I could always replace 8 with 6 and 2. I'm not saying that's the best thing I could do.
If we're decomposing 6 to 4 and 2,
Yes.
and then 4 to 2 and 2.
What I'm just saying is if I look at my optimal configuration, there's clearly not going to be any 6s because if there was a 6, I could do this. I'm not saying the best thing to do is to replace a 6 with 4 and 2. So I'm implicitly using a result from real analysis. If I have a continuous function on a compact set, then it does attain its maximum. I've got to be a little bit careful because this is integer stuff here. What I'm telling you here, though, is I'm not going to have any 5s, any 6s, any 7s, any 8s, and so on and so on and so on. And I might as well say that there's no 4s, because if I had a 4, I could just replace the 4 with 2 and 2. So we know each AK is either a 2 or a 3. Well, that's nice. So which would you rather have, 2s or 3s? We need a way of comparing 2s and 3s. Does this seem similar to any problem we've been doing in this semester? Yes, right? This is your advanced mathematical theory. We need to figure out what's the conversion factor between 2s and 3s. Well, for this particular problem, I care about the product of the numbers. For baseball, I cared about the expected number of runs scored. It's the same idea. I need a way to compare apples and oranges. How can I compare different things? So any idea about how to compare 2s and 3s? So we said before, a double and a triple was the same as a home run and a single in terms of slugging and on-base percentage. We said 2 home runs and a single was the same as 3 triples. What should I do for the 2s and the 3s?
You have to set it up like 2 to the x equals 3 to the y, or like some power ratio.
Well, I've got to figure out how many. I'm trying to decide between 2s and 3s, right? I've got to have a sum of s, right? So I have some number of 2s and some number of 3s, and the sum has to be s. What's the conversion factor between 2s and 3s? You know, before I want to have the same batting average. So we ended up having these equations for the number of triples versus the number of singles and home runs. And we figured out that, you know, for every 2 home runs, we had 3 triples and 1 single. What do I have for my 2s and 3s so it would have the same sum? How can I compare them? So how can I compare 2s and 3s? I need to get the same sum. So how can I have 2s and 3s giving me the same sum? So add a bunch of 2s, add a bunch of 3s. I want them to have the same sum. So let's solve 2 times x equals 3 times y. Right? So how many 2s do I need to have the same as the number of, to give the same sum contribution as some number of 3s? This is very similar to the equation we solved earlier. What's a good choice for y or for x? Try x equals 3, you get y equals 2. So 2 plus 2 plus 2 equals 3 plus 3. So 2 3 times is the same as 3 twice. What's the product here? So what would be the product of 2, 2, and 2? 8. What's the product of 3 and 3? 9. So basically, we want to have a bunch of 3s and then leftover 2s. If you ever have a leftover 1 at the end, then just kick the 1 into a 2 and make it into a 3. So basically, you have all 3s and either 0, 1, or 2 2s, right? And then there's only 3 things to check. Because once I have 3 2s, what do I replace 3 2s with? 2 3s. So there's only 3 things to check. So the fact that 3 plus 3 gives a product of 9 and beats 2 plus 2 plus 2, which gives a product of 8, this is related to one of the most important numbers in mathematics. So can you think of any numbers related to or near 2 and 3 that are really nice in mathematics? What number? So any good numbers in mathematics? E. So this is basically due to the fact that E is closer to 3 than it is to 2. This does not look like this. So again, the reason I wanted to do this problem is to talk about the general thought process of how do I compare different things. We were trying to compare singles, doubles, triples, and home runs. We wanted on base, slugging, batting average. Those were our constraints. And then we were trying to optimize something else. There's a huge area of mathematics. I do a lot of work in it called linear programming. It's a generalization of linear algebra. Linear algebra, you're trying to solve AX equals B. And if you have a square matrix, there should be one and only one solution if your matrix is non-degenerate. Trying to solve AX equals B, X equals A inverse B. And that's the only solution. If your system is underdetermined, it means you have more than one solution that's feasible, more than one X that will have AX equals B. And that gives you the chance of then optimizing. Of all the ones that satisfy all the requirements, which ones give me the best with something else? And so one of the earliest successes of this subject was the diet problem. When you're trying to design a diet, what do you think the most important thing about your diet is? And I don't mean diet to lose weight. The food you eat. What's the most important thing about setting up the food that you eat? It must do what? Fuel you, keep you alive. So if the only thing I care about is keeping you alive, that's not that hard. What else might you want to consider?
Like nutritional balance.
Well, so I will assume that if it keeps you alive, it has the right nutritional balance. I'll look at all the different diets that have the right nutritional balance to keep you alive. What else might I want after I have a diet that keeps me alive? What else might you care about? Taste. What else might you care about? Calories. What else? There's a big one that you're not thinking about. Anybody who's an economics major should be able to get this one. Cost, right? There are these wonderful diets that will allow you to lose a tremendous amount of weight if you have a staff of 6 chefs, working on you with incredibly great. Okay, most of us can't afford that. But once we have a diet that keeps us alive, we have all these other things we can try to optimize. That's what we were doing in the baseball problem. This is the general thing I want you to glean from this unit of the course, is that when I have multiple configurations that work, it opens up the opportunity of saying which one is best. And I have different choices of metrics. Now, when I have multiple things that I care about cost, taste, calories. How do I compare all those different things? This is why money is such a wonderful concept, is you can try to put cash values on these different things. When you're buying a house, what might you care about for the house? Size, location, maybe number of bedrooms. Maybe do you have a first floor bedroom? Might have an older parent who's going to move in and they don't need to do the stairs. That can be avoided. So you have to figure out how much is all this stuff worth. When you're trying to decide which plays to have on your team, you have all these different statistics. We want to try to convert them to something nice. How does this change your probability of winning? That's a really good statistic to look at. Wins above replacement. Wonderful statistic. Well, let's take this and let's adjust, generalize. So now each AK greater than equal to 0 is a real number. So we clearly have 0 less than equal to AK less than equal to S. Or is it clear? Well, yes, because we're adding them together, so nothing can be larger than S. So how many of you have done real analysis? It's not required. If you've done real analysis, this is enough for me to know that there is going to be an optimal solution. I can appeal to a result that says, if I have a continuous function on a compact set, would we ever want any of the AKs to be as small as 0? And if we're trying to look at maximizing the product, what's the smallest we can have. So if we want to maximize the product, what's the smallest one of the A's can be?
I don't think we would want anything less than one.
Good, nothing less than one, because if it's less than one, it's just lowering the product. So without loss of generality, one is less than or equal to AK. And what's the largest? Well, by the argument we did before, we don't want anything larger than 4. Because if it was larger than 4, we could break it up into 2 and then say, x minus 2. And that would be larger. All right, so what we want to do now is we want to optimize. And what we're going to do is we're going to break the problem up into simpler ones. So for each n, find the best, then find best n. So case 1, when n equals 1, it's easy. We just have a1 equals s. So case 2, when n equals 2, we have, say, x plus y equals s, and we want to maximize x times y, which is x times s minus x. So you might remember this as the Farmer-Brown problem from calculus. Farmer-Brown loves rectangles and will not consider any shape other than a rectangle. And you have a fixed semi-perimeter. You want to maximize the area x times y. So what object maximizes? Anybody know the shape? It's a square. And so we could see this by saying, let's let f of x be x times s minus x. And it turns out it's better to just expand it out. And now if I want to find where is this function maximized, I check the endpoints. F of 0 equals f of s equals 0. The critical points, I solve f prime of x, which is just going to s minus 2x. F prime of x equals 0 implies x equals s over 2. F double prime of 0 is equal to -2, so this is a max. So when n equals 2, the best I can do is to take a square. To some extent, you can almost apply this immediately to general n. Let's say we have a1 plus ... Oh, let's do it more slowly. a1 plus a2 plus a3 plus ... plus an. I'll put a star by all of them. Equals s has the largest product. What do you think should be true to have the largest product? So in the case of 1, we just had s. In the case of 2, everything was s over 2. What do you think is going to be the case here?
It's just S over N.
So the claim is each is s over n. So proof, if not all equal, make larger by replacing, say, AI and AJ with AI plus AJ over 2 and AI plus AJ over 2. So if I wasn't in the situation where they were all equal, if I take 2 of them that aren't equal and replace them, I get something larger. And I know that there is a maximum choice that exists, so that maximum choice has to have them all equal. Otherwise, I could just keep going. So this is where I need the result from real analysis, that there is a maximum. So we now get, for each n, the best is AK equals S over N, giving F of N is S over N to the N power. And find N that is best. Well, unfortunately, it's not so easy to find the N that's the best. So we have F of N is S divided by N to the N, but this is a function of an integer. And we don't have good tools to understand integers. So we extend. Let's study F of X is S over X to the X. So this is e to the X, the natural log of S over X. So we check the endpoints. That would be X equals 1, X equals S. I'm not going to do this in the interest of time, but it's going to be clear to see that if you have just one number, it's not going to be best. And if you make everything 1, it's not going to be best. So now we need F prime. So F prime of X, we have e to the crap. Whenever you take e to the crap, it's just itself times the derivative of crap. So I'm going to just get back F of X times the derivative of X natural log of S over X. So that's going to be the natural log of S over X minus X times the derivative of the natural log of S over X. Well, the natural log of S over X is the natural log of S minus the natural log of X. So when I take its derivative, the natural log of S is a constant, derivative of natural log of X is 1 over X. So F prime of X equals 0 means the natural log of S over X minus 1 equals 0. So the natural log of S over X equals 1. So what number has a natural log of 1? What number has a natural log of 1? No, 0, the natural log of 0 is undefined. E, the natural log of E is 1. So S over X is E, or X is equal to S over E. So the number of pieces we want to have is S over E. Each piece of size S divided by the number of pieces, which is E. So we basically want each piece to be of size E. Now the problem is this was finding the best real maximum. We want to find the best integer maximum. So remember, we have F prime of X was F of X times the natural log of S over X minus 1. That's the same as just writing it like this. And what I want to do is I want to just quickly talk to you about curve sketching. So here's 0, let's make it 1. And then we have the special point when X is equal to S over E. The derivative is 0 at S over E. When X is greater than S over E, the natural log of S divided by X over E is going to be the natural log of a number less than 1, so it's going to be negative. When X is less than S over E, I've got the natural log of a number greater than 1. What's true about the natural log of a number greater than 1? It's positive. So now I use some results from calculus. I love this problem because it basically requires us to use almost everything we know about calculus. I can do some curve sketching. The function has a positive first derivative up to S over E, and then it has a negative. So the curve looks something like this. So this is the real max. And then the integer max is either the floor of S over E or the floor of S over E plus 1. Because I'm going up and then down, it's actually very easy to optimize. All right, this gets us to exactly 1050. We just made it. I love this problem because it reviews so many things we're doing. But again, the big mathematical theme we're trying to do is how do we compare different things? We have the main thing we care about. I want the same slugging. I want the same on base. But now once we have that, we can ask a better question. I don't want just these to be the same. I want which one has the most productivity.